All right, so this is our first op-amp topology. It's called the inverting amplifier topology, or the inverting op-amp topology. Let me go ahead and just underline that, inverting. You'll see why it's inverting in a second. We're going to go ahead and derive the equation for the inverting topology, and then what we're going to do is, after we derive it, we'll go ahead and use that to solve an example problem. Okay, so I pulled this inverting amplifier topology figure straight from the textbook. I have it cited in the references slide at the end of this lecture video, just like I have all the other figures in this particular module cited. But what we're really looking at here is a configuration for the op-amp, which we see has two resistors connected. And like I said earlier in one of the previous videos, the op-amp behavior really depends on the kinds of components you connect around it and how you connect those components. Okay, so this is one particular configuration where we have a couple of different things going on. We have the plus terminal connected to some DC voltage. In this case, it's 0 volts. So I'm just going to go ahead and label this 0 volts. And this entire bottom is all going to be 0 volts. And then we have some voltage input V in right here. And so I know that the voltage at this node at least is V in. What's going to be the voltage at this node here? Well, if I remember my op-amp rules, my golden rules, it tells me that the plus terminal and the minus terminal have to be at the same potential. And if I know my plus terminal is at 0 volts, then my minus terminal ought to be at 0 volts also. So this is also going to be 0 volts, which is exactly what the figure kind of already shows here, is it's showing no voltage drop across these terminals, okay? And it even highlights the other golden rule for us, and that is that no current can flow into the op-amp input. So it's showing me that I have a current I1 flowing here through this resistor R1, and then I have a current I2 flowing here through RF. It's called RF because it's the feedback resistor, right? It's the resistor that we're using to feed our output back to our input side, right? That's what we talked about in the last lecture or the last video. And so since no current flows into the op-amp, I can do KCL at this node, and I can say that I1 is equal to I2 plus the current into my negative terminal, which I know is 0. So I can really just say that I1 is equal to I2, right? And so what I'm interested in this op-amp and in every other op-amp is I'm interested in finding the output expression, or some expression for the output voltage as a function of the other parameters in the circuit. So let's go ahead and write out the Ohm's law for I1 and the Ohm's law for I2. I know that I1 is going to be equal to the voltage drop across R1, right, divided by R1. And so that voltage drop, if I take a look at my circuit, I have a voltage VI on the left side and a voltage of 0 volts on the right side. So let me go ahead and just write that, VI minus 0 volts. And then I know that I2 is, let's see what I've got as my drop across RF. It's going to be some voltage on the left minus V out divided by RF. And that voltage on the left happens to be the negative terminal, so it's going to be 0 volts. So I'm going to go ahead and write 0 volts. And then I can set these two things equal to each other. I can say VI over R1 is equal to negative V out divided by RF. And so if I want an expression for V out, I can just get V out isolated by multiplying both sides by minus RF. And what do I get? I get that V out is equal to V in multiplied by minus RF over R1. And that can be rewritten as V out is equal to negative V in times RF over R1. And that right there is the expression for every non-inverting every inverting amplifier topology circuit. Okay, so if we ever see an op amp configured as such, where we have our input voltage fed into the minus side through a resistor, and then we have a feedback resistor connected in between, this is the inverting amplifier topology, and we can always use this equation here to determine our output voltage, okay? And you may not be wondering anymore why it's called the inverting amplifier topology, but the reason, if you are wondering, is because it inverts the polarity of the input. So if I have a positive output voltage, I'm going to get a negative, if I have a positive input voltage, I'm going to get a negative output voltage, and vice versa. If I have a negative input, I'm going to get a positive output. Okay, that is why it's called the inverting amplifier topology. This is the derived expression for the output voltage, and in the next slide, we're going to go ahead and use this expression to solve an example. Okay, go ahead and end this video here.